Okay, now let's discuss about the first approach, which is the observation approach. Okay, this one in this picture I already explained in the previous slide. Okay, this is the formula once you in condition 2, and then now let's discuss about the first approach to estimate our H is by using the observation. Okay, for observation, actually the approach is almost similar like you model the noise, okay, in the condition 1. Okay, in condition 1, what you do in order for you to model your noise, then you need to take a plane surface. Okay, the concept there is almost okay, that concept is also almost similar with or the approach or the mechanism there is almost similar to the mechanism that we will use in this approach, which is through observation. Okay, how to estimate our H, and then we know the fact that if you talk about the equation in frequency domain, this one and this one become multiplication. If you want to estimate the H here, then you can divide your G with your F. Okay, however, the issue is you need to remember the fact that the one that you can access is this one, okay, which is your G, but the one that okay, the F here you cannot access. So in other words, you cannot directly apply the multiplication because you don't have any information regarding how actually this F is look like. So that's why it's very difficult for you to estimate your H there. But another way you can do is that you can obtain some sample of the image where that image consists of your G and the estimated F there. So that's why we put here GS and FS. Actually GS, so what is GS and FS? Okay, let's see the slide. Okay, so how to estimate our H, then you need to compute by dividing our GS and F head S or FS here. Okay, doesn't matter is it F head or F here, it should be similar, it's the same thing. Okay, ideally we want to have F head equal to our F, so that's why it's the same thing. So how to obtain our F here? So for this purpose, then you need to capture image like this. In other words, if you have some image like this, of course this is your G, it's not your F. So what you do, you crop any or you take any portion, any small portion of the image that contain edge or boundary. Okay, for example this one. Okay, this small portion. So if you crop this point, of course this should be your G, and that's why we put here the notation GS, because why they use GS, because your G is the entire image. So GS S here is represent a sampling of the entire population. Okay, the entire image is the entire population. So if you taken small portion of the image, it's just a sampling of the whole population. So that's why they call it GS. Okay, so this is actually your GS. So what are the reason you are taken this edge? Okay, doesn't matter, you can take any edge or boundary that consists of some boundary or region that separate between one area with another area. Okay, that is edge or boundary. So you take any image that consists of that. For example, in this case we take edge at this place over here. Okay, once you get, okay, that is your GS. So the reason why we take the edge, because again, if you remember in this condition 2, the one that affected your image is blurring function or degradation function. So in general, why we call it blurring function, that is the one cause blur to the image. Okay, so in other words, the characteristic of blurring, or the strongness of the blurring inside the image can be obviously see at the edge. Okay, doesn't matter any image that you look if you looking into any image you will decide whether this image is blurred or not. You will see the edge or the boundary, because if the image is sharp, then the boundary is very thin, is very fine to separate between one region into another region, okay, as compared to another region. But if the boundary is a little bit you confuse which is the exact point to separate between this area and this area, then that is because of the blurring effect. So that's why the reason why we taken the edge region over here, because by having this kind of example, for sure you can estimate the f here. Okay, doesn't matter is half head or f, it's the same thing. Okay, if this is my image that affected with blurring function, okay, then I can just fabricate. Okay, this one is not the exact f, is a fabricate f. Okay, it's a fabricate sampling of f, because we know that there's a boundary there, but because of blurring effect, then we don't know what are the exact point that separate between this area and this area. So we just fabricate one image like this, which is the same size as this one, and then you just color this region with black, this one with the gray, the same color as this one. So we just decide the fine line that separate between this point and this point at this particular line. Okay, so now we have our, okay, now we already estimate or assume that we managed to access our the sampling of our f or our f head there. So now we already have my GS and we already have our f has. So what we do, so after that, then of course you already have, okay, you already have both, then you can estimate your h, because you already have this one. So that's why in the formula here, okay, one way you can estimate your h is to get the sampling or the crop version of your image, where that is your GS, okay, which is this one. And then once you get the h, or for sure you can fabricate or estimate your f there, fs here. So from there you can estimate your h, okay, because you have you can simply do this operation, okay. But of course, like the previous chapter, you cannot directly multiply, or sorry, you cannot directly divide this one just to get this one. Okay, seems like the previous condition 1, where you cannot simply minus between your G minus your noise to get your F. Same goes to this one. You cannot simply divide this one, because you already have this one, both this one and this one. If you can see here, if you convert this one into, you know, frequency domain, and this one into frequency domain, then you just can use this formula to estimate your H. Okay, once you get your H, then of course if you manage to get this one, you just inverse Fourier transform to inverse Fourier transform, so then you can get back your H there, or HS there. Okay, so but that is not happen, because you cannot directly compute the division operation like this. So what is the reason behind that? Okay, this is explained here. Okay, before that, this is this, okay, before that, before I explain that, this is the, you can see in the slide here, this is your GS, this is your FS that you obtain from this image. Again, like I said, when you apply, when you change into frequency domain, we model it, or we represent it in 3D form. Okay, we don't represent it in image anymore, because it's more meaningful to present this one in 3D. Okay, but this is just remember that this one GS over here is the frequency domain, or the Fourier transform, the output from the Fourier transform after you convert this one into frequency domain. And this FS, after convert into frequency domain, it become like this. Okay, now the issue is, if you put a cross section here, so if you just scan a cross section over here, and you plot the graph, same goes to this one, you plot the cross section, then you plot the graph, so then we can see some terminology like one-dimensional signals. So this is, look, this is your GS, this is your FS. Okay, so the fact is you cannot directly divide this one and this one directly. So the reason is because most of the time you can see that there's a point where your FS is 0. So if this one divide by this, if this GS is divide with the point with 0 over here, for sure you will get infinity. Okay, again, if you have some point over there, you divide with 0, you get infinity, which is make the system, you know, can provide some error because of high values there. So that's why it's impossible for you to directly implement such operation like this, because there's a point in Fs here is 0. So if something divided by 0 will provide infinity, which is very high value and impractical to do that. Okay, so that's why this approach is called observation. Okay, instead of you divide directly like that and provide the wrong answer or provide the wrong result there, what you need to do here is a better way to observe both GS and FS in order to identify difference between them. Meaning that instead of you divide together, you need to look into these two signals, which is the cross section of this one. Okay, doesn't matter, you can look here or you can look here, but better to look here because it's more meaningful. So that's why we try to plot the cross section. Okay, you need to see what are the difference there, and from there you try to estimate what actually again, like I said, in general, this is your F. So F here will go into your H, where your H will produce this one. That's the block diagram. So why we observe and see the difference? Because we want to see subjectively. Okay, that's why this approach is quite difficult, because it's very subjective. We want to see what are actually this filter or this H, which if the input is this one, it will provide this one. So if you can refer to this explanation. Okay, this one is from the Gonzalez textbook, because the author is after they do some observation, they come up with this statement there. Okay, you can see that what is Gonzalez said there. It's obviously see at the frequency 10 here. Okay, at the frequency 10 here, if you see at this point, it already distorted or it's already dropped, meaning that the frequency, meaning that this H over here is some sort like a low pass filter where the cut off frequency is 10. Okay, see the assessment or the estimation there is seem to be very subjective. Okay, because the author said that because you find out that at frequency 10 the value here is distorted or dropped, that's why it become very thin. Okay, but here is very high. So the author conclude that H over here can be estimated as some sort of low pass filter, because as you can see here, it will distort or stop the frequency which is lower than it will stop the frequency component which is higher than 10. Okay, and another conclusion that have been made by the author is that since this at the band stop here is keep ripple, so this should be this actually if this is ripple at the band stop, meaning that this H here is a low, not just some sort of low pass filter, is a low pass filter, is Butterworth low pass filter, because when we talk about the Butterworth, it will provide a ripple at the band stop. So that's how if we want to apply this approach, which is through observation, this is how it look like. It's very subjective, and you need to estimate subjectively by looking at these two components to estimate your H. Okay, so then from there in this book, if you refer to this book, it said that from here we can conclude that our H is a low pass Butterworth filter with the cut off frequency of 10. Okay, so so that's how they try to estimate that. So they conclude that that is our degradation function or blurring function can be modeled as Butterworth filter. Okay, so it's Butterworth low pass filter where the cut off frequency is 10. So this is how the estimated Butterworth filter looks like. Okay, so of course, this one again, like I said, is very subjective. But let's say this is the approach that you want to do. Actually, one of the things that I would like to give some advice is that, of course, the approach is very subjective. Meaning that, let's say you ask your friend to to access both to FS and GS, and they conclude a different way as compared to you. So what you can do is actually, for example, you can just estimate one like this one, cut off frequency 10, which is Butterworth filter. Then you can try to vary the after you model this one, and then you can try to stimulate back. Meaning that you take your FS there. Okay, you take your original FS, which is this one, you multiply with the estimate H that you have provide here. Okay, and then after you compute, you get your own G, and try to compare with this G. Okay, and try to find is it similar or not. If not similar, then you can tune the frequency. Meaning maybe you can reduce into cut off frequency 9 or cut off frequency 11. So then we can see which one is the best. Then you choose that one to be your H or H model. That's how you model your H. Okay, you do iteratively to find the best one. Okay, that is one way. Another way might be you can take estimation of other as well. You try to simulate and find which one is the best to represent your model by observe the result, and the one that close to your GS is the one that you choose to as your blurring function model. Okay, so that is how you do in this approach, which is called observation approach in estimating your H, where it's quite subjective.